Here we go. Probability models from observed data. Number one, Megan tells her friend that if she spins the arrow shown, it is a fact that the arrow will not land on the green section. Is she right? We'll take a look at that spinner there. There is a green section. Is it possible to land on that small green section? Yes, it is. It's absolutely possible. Is it likely? No. The purple section, the rest of the spinner, is much larger. So if we were going to guess, we would say that the spinner is going to land on purple. But is it absolutely 100% going to land on purple? No. There is a small possibility that it lands on green. So Megan is wrong. So let's find the answer that says that Megan's wrong. Is she right? No, because although it is probable the arrow will land on the purple section, it is not a fact. B says yes, because it's a fact the arrow will land on the largest area. C says no, because the arrow will land on the green section 50% of the time, and the purple section 50% of the time. And D says yes, because probability is fact. So clearly B and D are wrong answers, because Megan's wrong. It's not a fact that it's going to land on the purple section. It just probably will. So B and D are wrong. C is also wrong because it's not a 50% chance that it'll land on green and a 50% chance it'll land on purple. There's a much larger chance that it will land on purple. It's just not absolutely going to land on purple. So A is the right answer. It is probable the arrow will land on the purple section, but it's not absolutely going to. It's not a fact that it will. Number two, Elliot used a random number generator to perform a probability experiment. The numbers generated are recorded in the stem and leaf plot below. So if you don't know how to read a stem and leaf plot, here's how it works. If we have a random number generator, there's 6, 7, 8, 9, 10 on the stems, and then all these numbers are leaves. So the way you read this is, this first number here that says 1, and it's in the 6 row, that's the number 61. Then the next number, there's a 2, that's the number 62, because it's in the 6 row with the 2. The next one is also 62, because it's another 2. The next one is 63, then 64, 65, 65, 66, 67, 68. And that's all the 60s, because that's the 6 row. Now we have a 7. The first number in this row is 70. 70 makes 70. Then 71, another 71, 72, 73, 73, 73, etc., etc., etc. So that's how you use the stem and leaf plot. All the way down here to 10. 10 and a 0 makes 100, so 100, another 100, 101, 102, 103, another 103, etc., etc. So based on the information in the stem and leaf plot, what is the experimental probability that the next number generated will be 73? So if we're being asked for an experimental probability, we are going to look at the experiment that was performed and determine what the probability is based on the results of that experiment. What's the probability that's going to be 73? Well, how many 73s did we get so far? Here's my 70 row. I got 73, that's 1. Another 73, that's 2. And another 73, that's 3. So we got 73 in this experiment 3 times. Well, how many times did we do this experiment? How many total numbers did we gather? So we have to count these all up. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then there's another 10 and one more. That makes 21. Then there's 9 more right here. That's 30. Then 10 more. That's 40. Then 11 more. That's 51. So if you count all these up, you get 51 different numbers that were chosen. 3 out of those 51 were 73. So the probability that we're going to get 73 again, based on this experiment, is 3, because that's how many times we got it so far, out of 51. So it's the fraction 3 over 51. Pardon my messy writing. I'm trying to write with my mouse here. So 3 out of 51 is the fraction. Now, that fraction can be simplified because 3 and 51 both divide by 3. 3 divided by 3 is 1, and 51 divided by 3 is 17. So the probability that we're going to get 73 again is 1/17th. And the reason we have 1/17th is because we got 73 3 times, 1, 2, 3, out of 51 total attempts. 3 out of 51 is 1/17th. So we'll go ahead and find that answer. And there it is, C, 1/17th. Number 3, use the drawing tools to form the correct answer on the number line. A factory produces a certain number of dolls every day. The hair color of each doll is randomly determined. A sample of 240 dolls was randomly selected from a batch of dolls produced in one day. Of these randomly selected dolls, 48 were found to have red hair. Based on this information, calculate the probability of randomly selecting a doll with red hair from a batch of dolls produced in one day. Plot the probability on the given number line. So how many dolls did we have? We had a sample of 240 dolls. So a sample of 240 dolls means they looked at 240 of the dolls that were produced. From that sample, 48 had red hair. So the probability is whatever 48 out of 240 is. Now you're allowed to use a calculator, so I'll go ahead and get a calculator. Ready? And here we go. And the way that we calculate a probability, once we have our calculator, is we take the number that we found, 48. That's the number of dolls that have red hair. And we divide by the total number of dolls we looked at, which is 240. So 48 out of 240 means 48 divided by 240 in a calculator. We hit equals, we get 0.2. So the probability that we have a doll with red hair is 0.2, or 2/10, or 1/5, or 20%. So we're going to go ahead and go to the point tool, and then we'll find 0.2 on the number line, put a point there, and that's it. We're done. Number 4. Before placing an order, a clothing store owner surveys customers about their most preferred type of skirt style. The results of his survey are shown. So we have the skirt type, and we have the number of customers that preferred that type. So flare skirts, pleated skirts, A-line skirts, hoop skirts, skater skirts, and maxi skirts. Then the number of customers we have for each one of those is shown in tally marks. So this is 9 for flare, then we've got 15 for pleated, etc., etc. The question is, what is the experimental probability that the next customer surveyed prefers flare skirts? Okay, how many customers preferred flare skirts? We count the tally marks. Remember, every one of these tally marks has a slash through the whole group is 5, because you have 4 straight up and down tally marks, and then the 5th one goes diagonally across. So you can count that as 5, and then 4 more. So there's 9 right here. So 9 customers like flare skirts. That might be something when you're doing these problems, you want to jot it down, maybe write it on a piece of scratch paper. We've got 9 right here that like flare skirts. 9. That's a 9. Now we have to find out how many total customers were asked. How many customers did we have in this problem? It doesn't say. It doesn't tell us exactly. So what we have to do is we have to go through these and we have to add them all up. So we've got 9 flare skirts. How many pleated skirts? 15, 5, 10, 15. That's 3 groups of 5. So 15 right there. How many A-line skirts? 7. So there's 7. How many hoop skirts? 11 right there. 5, 10, 11. How many skater skirts? 9 also right there. So there's 9. And how many maxi skirts? 4. So these are all the totals for each individual type of skirt. We have to add them all up to get the total number of people that were surveyed. So let's go ahead and get our calculator out, make this easier on ourselves, and let's add these together. 9 plus 15 plus 7 plus 11 plus 9 plus 4 equals, there were 55 people that were surveyed. So the probability that they like the flare skirt is 9, because 9 people like the flare skirt, out of 55 total. So 55, 9 out of 55. And there's B right there. It says 9 out of 55. 9 out of 55, 9 55ths cannot be simplified because 9 and 55 don't share any common factors. 9 divides by itself and 3 and 1. 55 doesn't divide by 3. It doesn't divide by 9. It only divides by itself and 11 and 5 and 1. So they don't share any common factors. 9 55ths is as simplified as you can make that fraction. So 9 55ths is the answer. Let's keep it rolling. Number 5, Katrina and Tara are pulling billiards numbered 1 through 8 from a bag. Their results are listed below. So you've got a bunch of billiard balls here. And the ones Katrina pulled, she pulled 4 different ones. Her first pull, she pulled the number 1 ball. Second pull, she pulled the 8 ball. Third pull, she pulled the number 4. And her fourth pull, she pulled the number 6. So she did 4 of them. Now, Tara over here seemed to do the experiment way more times. She did it 16 times, and she got those results that you can see there. So whose experimental probability is closer to the theoretical probability of pulling out a billiard ball with a prime number on it? So how many prime numbers did Katrina get? 1 does not count as a prime number. 1 is not a prime number. Neither is 8, neither is 4, neither is 6. So if we were using Katrina's experiment, we would get a probability of 0 because she didn't get any prime numbers. So automatically, Tara is going to be the answer here. And that was the way we should have leaned right in the beginning because Tara pulled out way more billiard balls. She did the experiment more times. And if you want results that are close to the theoretical results, then your pathway that you want to take is doing the experiment more times. The more you do the experiment, the closer your results will get to the theoretical results. So we're going to pick Tara here. And there we go. Number 6, Audra rolled a 6-sided number cube with sides numbered 1 through 6 multiple times. Her results are shown below. Based on the data, so not based on the theoretical probabilities, but based on this data right here, based on her results, it says based on the data, what is the experimental probability? So not the theoretical probability, but the experimental probability. The theoretical probability, if you roll a good die, a fair, balanced 6-sided number cube, then the probability of each one of the numbers coming up is 1 out of 6 because each number has the same probability. But maybe sometimes there's something wrong with the die, or it's a cheating die. It's weighted, so it lands on one number more often than another. And in that case, you can roll the die a bunch of times and look at the experimental results, and you can find the probability that the next roll will be any one of the particular sides. So we're looking at it here. If we're going to find the experimental probability, we have to look at the results of the experiment, find how many times the number we're looking for came up, and divide that by how many times we did the experiment. So what do we want to know in this one? The experimental probability that the next time Audra rolls the number cube, she will roll a 2. So how many times did she get 2? In the times that she rolled the number cube, she got a 2 4 times. There's 4 right there. Well, how many times did she do the experiment total? Let's count all these up and we'll add them together. She's got 2 right here for the number 1. That's a 2. We already got the 4. This one happened twice, so there's another 2. My 2s are really ugly again. Pardon my writing. I'm using a mouse here. 4, there's 5 of them. She got 4 5 times, so she rolled the die, and she got the number 4 5 different times. She got the number 5 3 different times, and she got the number 6 9 times. So let's go ahead and add all those up. What is 2 plus 4 plus 2 plus 5 plus 3 plus 9? Again, you're allowed to use a calculator here. That's okay. So 2 plus 4 plus 2 plus 5 plus 3 plus 9. If you can do that in your head, great, but I'm not going to force you to. So 25 times we rolled the die, and she got the 2 4 of those times. So the probability is 4 out of 25. So which one of these says fraction 4 out of 25? There it is, C, 4 out of 25. 4 out of 25 is a simplified fraction, so that's our answer. Moving right along, number 7, Maria conducts an experiment in which she spins a spinner and records the section it lands in. The spinner has 6 sections, not all of which are the same size. So there's not the exact same probability that the spinner is going to land on each of these sections because the sections are different sizes. The results of the experiment are given in the table below. So Maria got red 12 times, she got purple 5 times, she got yellow 6 times, etc., etc. Match each section of the spinner with its corresponding experimental probability. So we're going to have to calculate the probability for each of the sections. We have green, blue, red, yellow, purple, orange. I'm just going to go ahead and throw them all right into the thing, and I'll put them in the same order we have up there. So actually, I'll put green last. I'll put red first because that's the first on the table. The order doesn't matter. You can put these in any order. I'm just going to match them up with our chart here just for simplicity's sake. Red, purple, yellow, blue, green, orange. So red, purple, yellow, blue, orange, green. I think I just said blue, green, orange, but blue, orange, green. So now let's calculate the probability for each one of these one at a time. First, red was 12. 12 out of what? Well, we have to go ahead and add those all together. So let's add up how many times we got each of the different, let's add all of these up together. So where's my calculator? We'll go ahead and just punch them in there. Start with red. We have 12 plus the 5 purple plus the 6 yellow plus the 15 blue plus the 20 orange plus the 2 for green. So 60. We're going to remember we did this experiment 60 times. So 60 was the total. So first up, red. 12 out of 60. So if we have the fraction 12 out of 60, what does that simplify down to? 12 out of 60. What do 12 and 60 both divide by? The fraction 12 and 60. Both 12 and 60 divide by 12. 12 divided by 12 is 1, and 60 divided by 12 is 5. So the probability for red is 1/5, because we got it 12 times out of the 60 total. And 12 out of 60, the fraction 12/60th, simplifies to 1/5. So we'll go ahead and find 1/5, and we'll put that next to red. Okay, next up, purple. Let's go ahead and calculate purple. It's still a total of 60. We don't have to calculate that all over again. We're going to have to remember 60. We're going to use 60 for every one of these, because when we added all the spins together, we got 60. So each one of these we're going to put as a fraction over a denominator of 60. So now purple is 5 out of 60. So we'll go ahead and write 5 out of 60 for purple. So here's purple. We got 5 out of 60. And what do 5 and 60 both divide by? What is that fraction if we simplify it? 5 divided by 5 is 1, and 60 divided by 5 is 12. They both divide by 5. So when we simplify 5/60ths, we get 1/12. So purple is going to be 1/12, and sure enough, that is one of our choices. 1/12 is right there for purple. Next one, yellow. Yellow was 6 out of 60. 6 out of 60, 6 and 60 both divide by 6. That becomes 1/10. Blue, 15 out of 60. They both divide by 15. That's 1/4. Orange, 20 out of 60. 20 and 60 both divide by 20. 20 divided by 20 is 1, and 60 divided by 20 is 3. And finally, green, 2 out of 60. Both divide by 2. 2 divided by 2 is 1, and 60 divided by 2 is 30. So there we go. Let's keep it moving. Number 8, a librarian has a box of books on 4 subjects: science, math, history, and reading. She conducts a probability experiment in which, for each event, she randomly picks one book from the box, records the subject, then replaces it. The results are shown in the table. So according to our table, she got the science book 40 times, she got the math book 16 times, she got the history book 20 times, and she got the reading book 36 times. Based on the probability model, how many books of each subject does she likely have if she has 28 books in the box? Now, according to this chart, we've got 40 science books that she chose, 16 times she chose a math book, 20 times she chose a history book, and 36 times she chose a reading book. But she doesn't have that many books in there. She only has 28 total books. Remember, she's picking a book and then she's putting it back into the pile. So the probability that she gets each one of these will tell us how many books there likely is in the total, in her bin of books. So let's start with science. If she chose the science book 40 times, out of the total number of times she chose a book, we can turn that into a probability. So let's go ahead and do that. Let's add all these numbers together to find the total number of choices she made, the total number of times she chose a book. So we'll start with 40. We're going to add 16, add 20, and add 36. So how many times did she do this little experiment? She did it 112 times. And she got the science book 40 of those 112 times. So I'll go ahead and write that down. We get the science book, so science, put the science in pink. So we get the science book 40 out of 112 times. So how do we know how many science books there are? If she got 40 out of 112 choices were science books, how many science books are there if there's only 28 books in the box? Here's how you find out. Reduce the fraction or turn it into a decimal. 40 out of 112. If you just go ahead and punch that into your calculator, you'll get a decimal. 40 divided by 112 equals, and we get this crazy decimal here. Don't worry about what the decimal is. It doesn't matter if it's super long like this one or if it's super short. Just leave it in your calculator. This is approximately 35.7%, but don't worry about that. Just leave it right here in your calculator. If she gets the science book about this amount of the time, then we would guess that about this much of the population is that particular science book. In other words, if about 35.7% of the time she's choosing a science book, then our best guess is that about 35.7% of the books are science books. So we just multiply this by 28 and we'll get close to a good number. So times 28. So what we're doing is we're taking that decimal, that crazy long decimal that we left in our calculator, and we're multiplying by 28, because that portion of 28 is going to be our best guess for the number of science books. And we do that, we get 10. So our best guess is going to be 10 science books. Now, you could have done that with fractions too, and it would have been a little prettier as far as all the math works out, because you wouldn't have gotten a crazy long decimal. If you simplify 40 and 112, you can set up a proportion where 40 out of 1 over 112 is equal to some number like x out of 28. So if you can solve this proportion, which you should be practiced at, then you can find the number x. And if you do that, you're going to find out that x is 10. 28 times 4 is 112. So what times 4 is 40? 10 times 4 is 40. So two of these say that there's 10 science books, C and D. So now we have to look at the other choices and figure out which one's which. Well, they both say 4 math textbooks, so looking at math isn't very useful. But C says that there's 5 history books and 9 reading books, whereas D says there's 9 history books and 5 reading books. Do we have to do our probabilities and look at our fractions to figure out which one's right? No, let's just use a little bit of common sense. How many times was a history book chosen? 20. How many times was a reading book chosen? 36. So what do you think there's more of? The history book or the reading books? Because we chose reading books more often, there's probably more reading books. So we're going to choose C as our answer because C has more reading books than history books. So we're going to choose C. Okay, number 9. Students drew one marble at a time from a box of marbles. The marbles were replaced after each draw. Students recorded the results of 25 draws in the table below. So you got that table there. It says on the first draw there was green. I know it's a little confusing looking, but it's okay if you just break it down. Draw is the number draw. So which draw? The first draw is draw 1. The second draw is draw 2, etc., etc. And then the color is what they got on that draw. So on the first draw, there was green. The second draw was blue. The third draw was green again. Fourth draw was purple. Fifth draw was red. Sixth draw was purple again. Seventh draw was red, etc., all the way up to the 25th draw. What is the experimental probability of drawing each of the 4 colors? So we've got 4 choices, and each of those 4 choices has 4 different probabilities. So let's pick a color and find the probability, and we'll start matching them up, okay? How many times did we get green? Let's count up all the greens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the probability of getting green is 11, because 11 of these answers were green, out of 25, because we did 25 draws. So green is 11 out of 25. That's the probability for green. Now, is that one of our choices? Which one of these says that the probability for green is 11 out of 25? So we'll go ahead and look for it. And we see probability green 3 out of 25, probability green 11 out of 25 for B. So maybe B is our choice. C says the probability for green is 3 out of 25. And D says the probability for green is 7 out of 25. So the only one that has the probability for green being 11 out of 25 is B. So that has to be our answer. Now, we could check the probability for the other ones just to make sure we're doing it right, not making a silly mistake. So let's check for blue. The probability for blue is 3 out of 25. So 3 of these should be blue. And sure enough, there's 1 blue, 2 blues, 3 blues. So blue is for sure 3 out of 25, and that's why it says 3 out of 25 right there. Purple should be 4, and sure enough, 1 purple, 2 purple, 3 purples, and 4 purples. And that leaves the rest for red, those 7 reds. 1, 2, 3, 4, 5, 6, and 7. Last but not least, number 10. Jamie, Lissa, and Drew each have their name written on a piece of paper in a bowl. One name is drawn at a time from the bowl. After each draw, the name was replaced. The results of 15 draws are recorded in the table below. Okay, so the first draw they got Jamie's name, and they put Jamie's name back, and then they did another draw, and they got Drew's name, and they put Drew's name back, and on the third draw, they got Lissa, put her name back. The fourth draw, they got Drew again, etc., etc. Here are the results for the 15 times they did this little experiment. So what is the experimental probability of drawing Drew's name? All you have to do is find how many times they drew Drew's name, and then divide that by 15, because they did the experiment 15 times. So how many times did Drew come up? Count them up. 1, 2, 3, 4. He came up on draw number 2, draw number 4, draw number 8, and draw number 12. So the experimental probability is that he will come up 4 times out of 15. So the fraction 4/15 is our answer. Because we can't simplify it, that's all you have to do. So that's it. Remember to work hard and reach out for help if you need it. And good luck out there.